All right, greetings everyone. Welcome to the first part of the video for section 4.6, our final section for this quarter. Kind of crazy how time flies when you're having fun, right? Yeah, I bet you agree with me. So in this section, we'll be looking at some applications of the exponential and logarithmic functions we've been looking at, and primarily applications of exponential functions, but we'll see how logs can be used to solve some problems with those. So we're going to start by looking at this problem that involves exponentials. So we're told that you go to the doctor and she gives you 17 milligrams of radioactive dye. After 24 minutes, 5 milligrams of dye remain in your system. And to leave the doctor's office, you must pass through a radiation detector without sounding the alarm. And then we're told that the detector will sound the alarm if more than 2 milligrams of the dye are in your system. So we want to know how long your visit to the doctor will take, assuming you're given the dye as soon as you arrived. And we're told to assume that the amount of dye in your system decays at an exponential rate. So being that we're told that it decays at an exponential rate, we know we're going to be dealing with one of our formulas for exponential functions. So either the f of x equals a times b to the x, or f of x equals a times 1 plus r to the x, which kind of clues you in on what we need to start with here before we can even solve this problem, is we need to create an equation of some sort, right? And I will tell you we could use either one of these forms for an exponential, but in this case, the first one will be most useful for us. And recall that we use this one, this form, this f of x equals a times b to the x, when we have 2 points we can work with. So let's see if we can come up with some points based on the information we're given here. So first of all, we're told that when you go to the doctor, you get 17 milligrams of radioactive dye, and we're told to assume that happens as soon as you arrive. So how could we make a point from that? Well, I'm going to make that the point 0, 17, and let's think about what that means, right? We're told that you're given the dye as soon as you arrive, so does that make sense why this 0 is here? Right, because it happens at time 0. And at time 0, the amount of dye in your system is 17 milligrams. All right, then looking at the other pieces of information we're given, we're told after 24 minutes there are 5 milligrams. So that tells us we'd have the point 24, 5. So after 24 minutes, there are 5 milligrams. All right, then we can use this information to come up with our equation. And notice from these points, we actually already know the value for a. That's going to be 17, because that's our starting value. So we know our equation will look something like f of x equals 17 times b to the x. We need to solve for the value of b. We can do that using our other point. So we have 5 equals 17 times b to the 24th in this case. And we'll go ahead and solve for b. So we'll divide by 17 on both sides. So 5/17 equals b to the 24th. And then, even though this will look wonky, we'll take the 24th root on each side to undo that 24, that exponent of 24. When we do that, we end up with b equals the 24th root of 5/17. So we'll go to our calculator, or I'm going to my calculator right now and plugging that in. And I get 0.950, or just 0.95 from that. Okay. There we go. All right, so now we know the values for both a and b. We can use that to write our equation then. So it would be f of x equals 17 times 0.95 to the x. And now we can go ahead and solve the problem, right? So we want to know when
We get to 2 milligrams of dye, so we can leave. And notice in the way we set up our points before, we had time as our input, so that'd be our values for x, and the amount of milligrams as our output, so f of x. So since we want to solve for time, we need to solve for x, so we'll set the milligrams as the f of x. So we have 2 equals 17 times 0.95 to the x. We'll divide by 17 on both sides. We do that, and we end up with 2/17 equals 0.95 to the x. Notice we're solving for the exponent here, which means we need to take a log on both sides. Okay, when we do that, that allows us to move the x out to the front. Just become log of 2/17 equals x times the log of 0.95. And we can divide by log of 0.95 on both sides. So we see that x equals log of 2/17 divided by log of 0.95. So then we can go ahead and plug that into the calculator, which is what I'm doing right now. And when I do, I end up with 41.722. In this case, our units are minutes. Okay, so it looks like our appointment will last about 41.722 minutes before we can safely leave. All right. As always, if you miss anything, please make sure you go back in the video and rewatch it. All right, moving on. Let's talk about half-lives. So the half-life, it says here of a radioactive isotope, but really of anything, is that it is the time it takes for half the substance to decay. So basically, if you start with an amount, it's the amount of time after you'll have half of that left. So if you think about, a liquid in, say, a beaker or a cup that's evaporating, the half-life would be the amount of time it takes to get to half of what you started with. And in the case of something evaporating, that's probably going to take a while. All right, so let's look at an example of this. So we're told that the radioactive substance methanium, which is definitely not made up, decays following the equation f of t equals 100 times e to the negative 0.036 t, where t is in years. And we're told to find the half-life of methanium. And again, this means half-life means the amount of time it takes to get to half of what you started with. Now, in this case, they didn't give us any amounts of methanium, right, and told us to figure out how long it takes to get to half of that amount. But if we analyze our equation here, right, we can get something from this 100, because that 100 is in that place. And notice it looks like we're dealing with continuous decay here, so this is something of the form f of t equals a times e to the rt. So that 100 is in the place of a. And do you all recall, what does a stand for? Right, that stands for our starting value. So if we want to find a half-life, we can just figure out how much time it gets to half the starting value. And so if we start with 100, and we're not actually told what the units are, let's say they're grams, then half of that would be 50 grams. So what we need to figure out is the amount of time it takes to get to 50 grams. So we can set up an equation like 50 equals 100 times e to the negative 0.036 t. And hopefully it makes sense that we'd have t as our variable since we're trying to find the amount of time in years. So we can go ahead and solve that. Divide by 100 on both sides. So then we'll have 50 over 100, which we know reduces to 1/2. So 1/2 equals e to negative 0.036 t. Now, since we're trying to solve for something in the exponent, we need to take a log on both sides, but since we have an e here, I actually want to use the natural log.
Okay, when we do that, now we can move our exponent out to the front. So when we do that, we'll now have ln of 1/2 equals negative 0.036t times ln of e. But recall, ln of e just equals 1, since we know ln is like log base e, so we're asking to what power do we have to raise e to get e, and the answer is 1. So this really just becomes 1 times negative 0.036t, which is just negative 0.036t. And then we can solve by dividing by negative 0.036 on both sides. Okay, and when we do that, we end up with t equals, again, plug this into our calculators, and looks like we get 19.254, and in this case, the units, as we saw above, are years. So it looks like the half-life of Mathanium is 19.254 years. Okay, now here's the interesting thing about a half-life, is it doesn't matter what amount you start with. So we said we started with 100 grams, we figured out the amount of time it would take to get to 50 grams was 19.254 years. But let's say we'd started with 60 grams. Okay, and I kind of wrote that over here in the corner. Well, if we want to figure out how much time it takes for that to get down to 30, well, it turns out that's the same. It would still be 19.254 years. And in fact, if we wanted to go down from 30 to half of that to 15, the amount of time would still take 19.254 years. So again, half-lives are kind of constant. Doesn't matter what amount you start with. The amount of time it will take to get to half of that amount will always be the same. All right, that's it for now. Thank you for watching.